Welcome, fellow chemists, to a continuation of the reactivity-selectivity principle, which we will use to predict product distributions. Some of the numbers we require were introduced in the first video, so please watch that to refresh your memory if necessary. So let's recap where we left off with monochlorination. With more primary hydrogens on the molecule than secondary, random chance would result in a product distribution of 75 to 25% in favor of the primary halide 1-chloropropane. The 4-to-1 difference in reactivity of chlorine should result in an 80 to 20% distribution in favor of the secondary halide 2-chloropropane. However, we also know that the experimental distribution is somewhere between these two extremes. This means that to explain the result, we need to account for both the probability and the reactivity of the halogen. This is going to involve a bit of maths. On this molecule of propane, there are 6 primary hydrogens and only 2 secondary hydrogens. Chlorine's reactivity on primary positions is considered 1, while that of secondary positions is 4 times higher. If we multiply the number of hydrogens by the reactivity, we will get a product 6 for primary and 8 for secondary. We add these numbers together to get a relative total of 14. The 6 primary hydrogens accounts for 6 of that total of 14, or 43%. While the secondary is the remaining 8 of 14, or 57%. And this calculation closely aligns with the experimental results. So now let's try and figure out what happens with bromine. The probability of bromine landing on one of the 6 primary positions is 75% and 25% for the 2 secondary positions. Based on the rates bromine forms primary and secondary radicals, we would expect 98.8% of the product to be 2-bromopropane. However, once again, the experimental distribution does not match either the probability or the reactivity predictions. So if we perform the same type of calculation for bromine that we did earlier for chlorine, we should end up with a distribution that closely resembles experimental results. So we already know this part. There are 6 primary hydrogens on propane and 2 secondary hydrogens. Bromine's reactivity on primary positions is considered 1, while that of secondary positions is 82 times higher. If we multiply the number of hydrogens by the reactivity, we will get a product of 6 for primary and 164 for secondary. Adding those together gives us a relative total of 170. The 6 primary hydrogens accounts for 6 of that total of 170, or 3.5%, while the secondary is the remaining 164 over 170, or 96.5%, and this again closely aligns with experimental results. Before I show you the predicted product distributions for chlorination and bromination of 2-methylpropane, pause the video and give it a go. First up is monochlorination, and we need to count our hydrogens. On this molecule there are 9 primary hydrogens, and there is a single tertiary hydrogen. The relative reactivities of chlorine on these positions are 1 and 5 respectively. The products of the number of hydrogens times the reactivity are 9 and 5. We add those products together to get a sum which is 14. In order to determine the percent, we take the individual products and divide them by the sum and get 64% for the primary product and 36% for the tertiary product. The major product is primary because there are more primary hydrogens for the not too picky chlorine to substitute. Now switching to bromine, the number of primary and tertiary hydrogens will of course remain the same. The reactivity of bromine on the primary position is 1, but for the tertiary position it is 1,600. When we multiply the number by the reactivity, we get 9 and 1,600. This gives us a total of 1,609. To calculate the percents, we take the individual products and divide them by the sum, which will be 0.6% for primary and 99.4% for tertiary. Bromine is more selective than chlorine and almost always substitutes for the tertiary position over the primary position in this case. For the final practice, predict the product distribution for the halogenation of methyl cyclopropane. Pause the video and give it a go. This is the first molecule we are seeing that has all 3 types of hydrogens. It has 3 primary, 4 secondary, and 1 tertiary. We know the reactivity of chlorine on these positions, and it is 1, 4, and 5 respectively. We multiply the number by the reactivity to generate products, which are 3 for primary, 16 for secondary, and 5 for tertiary. These numbers indicate that it is probably the secondary product which will be the major one. To see if that is the case, we add the products together to get 24. And we use that sum to divide all the individual products in order to get the predicted distributions. We get 12.5% for primary, 66.6% secondary, and 20.9% tertiary. Our hunch was correct that the secondary product was produced the most. When we switch to bromine, the number of primary, secondary, and tertiary hydrogens will remain the same. The reactivities on those positions, though, are 1, 82, and 1600. When we multiply those reactivities by the number of hydrogens, we get 3, 328, and 1600. Clearly, we would expect the tertiary product to be the major one for the bromination. The sum of the products is 1931, and we use that to divide the individual products in order to determine the percents, which are a measly 0.2% primary, 16.9% secondary, and 82.9% tertiary, which confirms our suspicion that the tertiary product is the major one. And to summarize these calculations, we first need to identify and count any primary, secondary, and tertiary hydrogens on our alkane. These are the locations where the chlorine or bromine will substitute. We find the reactivity of the halogen towards those particular locations. We then multiply the number of hydrogens by the respective reactivity of chlorine or bromine towards them. We add our products to get a sum. We then use this sum to divide each of the location totals by in order to determine the percent of product distribution. The percentages we calculate should closely resemble experimentally determined distributions. In part 3, we will explore the results if the molecule contains multiple, unique, but chemically distinct primary, secondary, or tertiary positions. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. Since this video contained many numbers, today I shall recommend a channel all about them, Numberphile. After today's bit of serious maths, enjoy a recreational or not foray into the numbers to learn how infinity is bigger than you think and to learn the optimal way to stack your cannonballs. You will find links to the channel and website in the description. However, also check out the mechanism behind radical substitution now that you know how to predict product distributions. As always, feel free to get in touch with me via email, social media, or if you would like, make a request in the comments.